We are recording with the one, the only, Mr. Richard Rhodes, who's been on here several times before. I get giddy talking to you. I always get a little starstruck, and I have to stay cool. I've read your books, Making of the Atomic Bomb, and specifically Dark Sun. I've probably read Dark Sun, no kidding, probably 15 times. I truly love that book. You've been on here
I
before. We've
think
done.
it's the better. I
Excuse
think
me.
it's the better of the two. I really do.
It's a masterpiece. I mean, I love all of your. You've come on here. We've talked about energy. We've talked about scientists. Uh, we've talked about, another book I always recommend to a ton of people is Masters of Death, about the SS Einsatz group, and that was it's one of the more life changing books I've read in terms of human psychology. We've talked about the psychology of fear and of killing and all of that, and we did 3 episodes on energy, which starts in the Shakespearean era and goes all the way up through oil. And you and I have kind of gone back and forth about nuclear fission and then the holy grail of fusion. And when we
Yeah.
last spoke, you said you're going for a trip to go actually research some fusion, and that was several months ago. And so with that, I will stop talking and have you please take it away and educate me and my audience about your travels.
Well, the fusion part never developed. I don't know what happened. Somebody dropped the ball, but I didn't get down to the south of France, excuse me, where they're building a large tokamak reactor that
Mm-hmm.
I think a number of European countries are contributing to. What I did do, because I'm working on a book right now about particle physics, was to go to Switzerland and visit the world's largest machine, which is a 27-kilometer circumference particle collider at CERN, the European Laboratory for Particle Physics, that's buried underground but across the border between Switzerland and France, and which is the one that discovered back in 2012 a very elusive particle called the Higgs boson, which
Mm-hmm.
I'll talk about in a second. But this machine is literally colossal. Not only the underground pipe, which isn't that big, but which is certainly long enough, God knows, 27 kilometers, about 17 miles in circumference. But the collecting part of the machine, which is called Atlas, some kind of acronym that I did memorize, is about the size of let's see, an oil tanker.
Oh yeah, I've
It's,
seen
it's a
pictures of it.
cylinder. It's a cylinder about 6 stories in diameter, packed with all sorts of collectors and detectors. So this machine accelerates using superconducting magnets, another whole amazing piece of technology. Accelerates protons. They showed me the little tank, which is about the size of a little beer tank, the kind you take on when you go to a picnic. They said that's our annual supply of hydrogen, from which we make protons by stripping off the electrons of hydrogen atoms. And this giant machine is all about accelerating these protons till they're going very close to the speed of light. And two beams running in opposite circles within the same underground pipe system. And then when they're at their maximum velocity, they collide them. They also squeeze the beam down to a diameter of less than the thickness of a human hair. So they're very dense with particles because they want them to smash into each other. And although there are some millions of protons in each aspect of the beam, they still are so small. You really have to squeeze them in close proximity to get them to collide. And they usually don't get more than 5 or 10 collisions in any one pass with this beam. Well, when you accelerate a particle, you increase its mass. To say it in a simpler way, it gets heavier.
Yeah.
So by the time they're going very close to the speed of light, they're very heavy. And when they smash into each other, they just fragment into all sorts of subatomic particles, quarks and gluons and all of these very exotic particles that have been discovered in the last 50 years. Uh, and these things go squirting out sideways into this giant tank car of a collector around them. And it sorts them as best it can according to various qualities they have. It's just the most amazing machine. And when you think about how big it is and how precise it has to be, it's a marvel that they were able to build it at all.
What the what were the old? There's some old. I forget how they did it. I think you and I talked about it. Like the early particle researchers. I mean, I want to say like I don't know, 1920s, 30s, or something. And they would use these
Yeah.
like oil on metal, and they had these. Have you seen those pictures? And it's just like the swirling loops, the originals.
The first colliders, not colliders, the first particle accelerators were linear. And then one of the early ones, that probably the most famous of all, was the cyclotron at Berkeley. And I saw the original cyclotron, which was a little glass uh, tank about 4 inches in diameter that had some little coils of wire in it and some magnets on it. That's where it all started back in the 1930s at Berkeley under a guy named William Lawrence, who was not a great physicist, but he was a great machine maker. So he kept building bigger and bigger cyclotrons. And as you get particles going, you have more problems keeping them where you want them.
Mm.
It's easy enough, although not that easy, just in a straight line. But if you want a particle to go around in a circle, obviously you have to keep it continually uh, changing course as it goes around. And as it goes faster, it gets heavier. So the magnet has to be stronger. And it gets to be quite complicated. But they solved those problems one by one. And after the Second World War, when Europe was just destroyed pretty much, and some of our American bomb guys, particularly a man named Isidore Rabi, one of the Nobel laureates who worked on the bomb, he was concerned that if the scientists of Europe didn't have anything better to do, they might get busy with their countries working on nuclear weapons. We didn't want to see weapons proliferate all over the country, all over the world. It was bad enough that we knew the Russians were working on them. So he proposed, and others came in as well, the idea that there would be an international European laboratory for particle physics, which was the new field that needed the most development. And the governments of Europe decided that was a good idea, as did our government. And they put the money together to build CERN. CERN then started building larger and larger cyclotrons, basically. Mm-hmm. They had different by then, but they were still circular. Well, they all had one problem, which is if you fire a particle into a stationary target, most of the energy is wasted just stopping the particle. And it doesn't necessarily go into making more particles or crashing something and getting more energy out of it. So some guys started thinking about colliding particles, having two beams and not just one, having them circulate in opposite directions and then colliding them in the middle. And there, of course, almost all of the inertia of the two particles gets used up smashing each other.
Yeah.
And you get a much higher energy production and therefore more results. That was basically the idea for these colliders. And this one is now the largest in the world, although it won't be for long. They're planning now to build another one. These have all been built in the same place, in a valley.
Yeah, they're like within each other.
Between the Alps and the Jura Mountains. And the next one is going to be 100 kilometers around. It's actually going to surround the city of Geneva, underground, of course, way underground, 100 meters underground. And the ones that they've built previously, many of which are still in use, because they didn't stop being useful just because they weren't the most powerful, will just be feeder. We'll start the acceleration going and get it up to a certain point so they don't have to go from 0 to almost the speed of light in one big machine.
Oh.
So the old ones have if you look at the pictures from the
Yeah,
air,
they're
you
all
see
yeah, they're
these
like
rings all
they're all touching each other.
attached to
Yeah.
each other. Yeah, exactly. Right.
Yeah. It's not
So the next one is going to be even more. I don't know what they're going to find, or if they know what they're going to find, but they figure they'll find something. When this machine started operating in 2008, uh, well, once they really got it going and got it up to the point where it was at its maximum acceleration, somewhere around 2018, they weren't getting any new particles out of it. And there was a kind of a quiet panic for a while that maybe they'd reached the limit. Maybe there weren't any more particles. You can think of this machine in another way as a kind of a way of looking back in time to the period right after the Big Bang,
mm,
because the Big Bang produced just this enormous flush of energy, and particles precipitated out of that field of energy at very, very high energies. So you can say we're closer and closer to the conditions at the time of the Big Bang. This accelerator, the Large Hadron Collider, the one I went to see, is able to produce particles with energies within a trillion of the time of the Big Bang. Because, of course, once the bang exploded, they started slowing down,
mm-hmm.
cooling, if and so the ones they're making now take us almost all the way back to the moment when the whole universe started. I don't quite know how one that's going to be what 4 times as large as the one they have now is going to get back another fraction of a trillionth of a second. But a lot of stuff went on when the big banged, as it were. And they're getting closer and closer to those conditions, and therefore learning more about what was happening at the beginning of the universe before there were even particles, because there was such an intense mass of energy in a small space that they hadn't even precipitated out yet, as it were. I'm at the edge of my understanding of all of this when I talk about it. So,
hey, well,
but
your edge is beyond my
my return,
understanding.
I had to get this trip out of the way, and it was kind of inspiring. But I have so much more to learn.
Yeah.
Just beginning.
Yeah, I mean, I would imagine that I guess it's almost, I guess, on the topic of nuclear weapons, like your books. It's like if you ever watch a video of just one of the old A-bomb videos or hydrogen bomb videos.
Yeah.
You hit play, you see the ocean, there's the flash, the explosion, and the mushroom cloud. But let's say the video is 60 seconds long. Second 10 to second 60, there's only so much change. But second 9 to 10, there's more change. And then second 8 to 9, so at the very beginning you have this, it's a flash. You see the double flash, and then like the little ball on top, and then the shock wave, and then the change slows down. So I would imagine as they push back to maybe only a fraction of a trillionth of a second further, it's probably, I would imagine, it would yield a novel amount of more information, because much like accelerating something to the speed of light, it becomes heavier and heavier and heavier. There is almost like this, it's like the inverse of diminishing returns. It's exponential returns. As you just get just a fraction of a second back, the new information is even more novel. And so it's got to be worth it, I would think.
Well, I've been reading a series of lectures the last couple of days by Richard Feynman, the famous crazy wonder physicist with a marvelous sense of humor, who was a Brooklyn guy and who was really not a snob. You can meet plenty of snobs in any line of work, and he was just determined never to be a snob. So these lectures, which he gave at some prestigious forum in England back in 1964, were ad lib, and they were transcribed and then I guess straightened up a little bit. But it's him talking in his kind of Brooklyn patois about about how physics works and how science works. They're really clever and wonderful, but he talks a lot about one of the things he says, for example, is nobody understands quantum mechanics. he, which is just a marvelous statement since quantum mechanics has been the field of physics that is at the cutting edge
Yeah.
and has been since the early 20s, really, but mostly after the Second World War, and is intimately related to all these issues about particles and where they go and what they do and how they're created and how they transform and so forth. It was, originally everyone thought there were two particles, electrons and protons. The protons were the nucleus of the atom, the electrons were the sort of planets circulating
Yeah.
around that nucleus. And then they figured out that there was also a neutral particle called the neutron, which made it much more possible to look into the interior of the nucleus of atoms, because the nucleus of atoms is electrically charged. The proton has a positive charge. So if you try to hit that nucleus with protons, they're repelled and you don't get much effect from the collision. In a way, it's interesting that they're colliding protons with protons in the Large Hadron Collider, the LHC, because there is a repelling force. But of course, obviously, they've accelerated everything to such a high rate that they can smash them together and actually get them to mate and do things. Anyway, then the neutron was discovered, and the neutron could just slip into the nucleus of an atom. One of the scientists who was working on them in the 30s said, in fact, it was Robbie, the guy I mentioned earlier, who was a really wonderful scientist and clever guy. Robbie said it was almost as dramatic as if the moon had smashed into the Earth. And of course, it was the neutron that made it possible to discover nuclear fission, the fission of the uranium atom when you just bombard it with a few neutrons. And since it's right at the edge of falling apart anyway, the last natural element on Earth, just barely hanging together, there's another force inside of the nucleus called strong force that holds the nucleus together. Otherwise, all those protons would have just drifted apart long ago. So they're really, but there's a limit to how much the strong force can hold all these protons together in a uranium atom, and the uranium atom is about at that limit. So you drop in a neutron going at just ordinary room temperature, barely moving, and the uranium atom starts wobbling around like a bag of water of the kind we used to throw off the roof and hit people in the head with. Anyone's ever played with a water-filled balloon has a sense of what a uranium atom feels like or would feel like. So that made it possible to produce the phenomenon called nuclear fission, and off we go. And after the war, when we wanted to reward all the guys who had worked on the bomb, all these physicists who had stopped their graduate study or stopped their teaching and research careers in order to do this war work, excuse me, the reward was they got to build any machines they cared to build. The government was going to pay for them. And thus, really bigger and bigger versions of the cyclotron got built out at Berkeley in California, and a new lab was started in Brookhaven on Long Island, and another one was started up in Chicago, outside of Chicago, called Fermilab, which is still there and still operating. These were all the fruits, if you will, of rewarding our guys for producing the atomic bomb. In the meantime, Europe is doing the same thing because they want to keep their scientists busy. The Russians are not doing as much because it's harder to convince guys like Lavrenti Beria, the head of the bomb program, but also the head of the KGB, that was worth their money and time. So they're mostly working on bombs. They finally get to working on thermonuclear fusion machines in the 50s. And Sakharov, of all people, the one who really invented the Soviet atomic bomb and hydrogen bomb, builds the first of a type of machine called a tokamak. This is what we were talking about earlier, which is a donut-shaped
Hmm.
machine that moves the plasma of that's inside this machine around and heats it by squeezing it with magnets, hoping to get to the point where you can fuse hydrogen and helium atoms together and make energy. So this all came out of that period after the war when the question was, oh my God, scientists aren't just blue sky guys up in towers. They can build horrible weapons. We've got to find something for them to do. And these are the fruits of all that work. And although it's hard to say what on earth the value, other than for general knowledge, there is in colliding protons together at nearly the speed of light, all sorts of strange things come out, and who knows? So that's where things are now.
Yeah.
Fine. Go ahead.
No, no,
Yeah,
keep
go
going.
ahead. I was just going to say Feynman is really wonderful in talking about how physics works. And I'm trying to puzzle out, without having any math, what on earth quantum mechanics is about. And he makes it a lot simpler. There's this thing that everyone's probably heard of called the how is it usually called? Well, the idea is if you run a beam of light particles at a
Double
screen
the
that
double
has
slit
two,
experiment.
yeah, it has two holes in it. There are circumstances where you can't figure out which hole a particular particle came through. And he explains that so simply. He says, that's because you can't know that. He said, I know that that works against everyone's common sense feeling that everything can be known. But the fact is, if you try to know it, you make it go through one or the other. But you can't turn out the light and somehow figure out which one it's going through. It'll go through whichever, it'll go through both, he says, as far as you could possibly tell by any way of measuring. It'll go through both at the same time. He says that's how crazy quantum physics is. And that makes it easier to accept when a guy with the horsepower of Dick
Feynman.
Feynman is able to say, we can't know that. We don't know that, and there's no way to know it. So forget about it. Just move on. We'll think about something else for a while. It's nice to hear.
Yeah. 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 If some world class athlete tells you that there's no way to run a 3 minute mile, you don't feel so bad that you can't
Excuse
do
me.
it. No, you're good. Richard Feynman is years ago. I remember watching some of his lectures, and he was kind of just sitting in a big chair, and he would talk about things and just yeah, no, you could see him is that he was just there was like a goofiness about him. And he would
Yeah.
start laughing about like the size of the universe. It was, he was like, it just starts making you get nutty. And like, and he would always, yeah, the opposite of a snob. It was more of like, he wanted to welcome you into his world and be like, look how crazy this is. There was no snobbery.
Yes. And some people will have heard of him because of what was probably his most famous political participation, which was in the question of what happened to the Challenger spacecraft,
Mm-hmm.
the Challenger that blew up not long after takeoff
Yeah.
and killed 7 people aboard. Uh, he was on the committee that was assigned by Congress to the commission to try to figure out what happened. And there was a lot of back and forth and so forth. And what he did was take a piece of, what was it,
The O ring.
of the material that was used to make the siding on one of the tanks. There was the lining, some sort of rubbery material that was lining one of the fuel tanks. And because the question was it something that would have gotten rigid at the low temperatures that morning on Cape Canaveral, Cape Kennedy, to the point where it cracked under the freezing effect of all that liquid
Mm-hmm.
oxygen that was in the tank? And everybody was debating it. And the guys who built the tank were saying, nah. He quietly went out during lunch and got a glass of ice water, took a bit of the material and dropped it in. left it in for a while, pulled it out, and showed that it would crack, showed that it was hardened by the cold. That was the kind of thing that Feynman would do often. He was a superb experimenter because he could think of things in a clear way. He's the guy who, in the midst of all of the very complicated mathematics of quantum mechanics, very complicated partial differential equations, things I have no idea what they are, Feynman figured out that you could do a little sort of a cartoon drawing that would symbolize the actions of a particle colliding with another particle. And by using, let's say, drawing a spiral arrow going one way and a dotted arrow going another way, you could not only show what would happen with the various particles that came out of the collision, but you could also indicate what kind of particle they were, what they were doing. There was another guy equally really brilliant with Feynman, but a much more formal physicist who was just offended by Feynman's diagrams. And they've become absolutely the standard model for people learning this kind of physics because they're so clear. It's just like looking at a little cartoon drawing. And they don't tell you everything. And of course, there's more to learn, but at least they enable you to visualize in a very simple way these rather complex actions that go take on when particles collide. So another Feynman story that I like that isn't usually told, he's famous for picking all the combination locks at the security safes at Los Alamos. And he probably did that too. He figured out very early on that most people, when they're given a safe, never reset the combination, which is usually set at 0, 0, 0, 0, 0. He'd go around and pick half of them just by turning everything to 0. And then the others would be a little more complicated, but not that much more, because as with passwords, there's an inverse relationship between the complexity of the password and whether you can remember it or not. A constant problem for me. I'm old enough that my memory doesn't work that well. So Feynman's well known for those things. What he's not so well known for is things like he was one of the fundamental physicists who worked out quantum mechanics, first of all, and his Nobel Prize was for that. There are stories that some of his colleagues tell that I think indicate just what an original and a brilliant man he was. They would go to him with a new idea they had that they'd already worked out the mathematics on, and it was an original idea. It was brand new. And he would say, wait a minute. He'd go to the drawer of his desk and he'd shuffle around at the papers inside and pull one out and hand it to the guy. And it would be the same idea, only he hadn't even thought it was important enough to publish. He just thought it up and written it down and thrown it in the drawer.
Just
I would talk about devastation. that would be 10 years with a shrink.
Yeah.
But that's what he was. So
having this brilliant realization, maybe this happens, and so you bring it to him. He's like, oh yeah, no, I wrote that on a napkin 3 nights ago when I was drunk. Yeah, no, I thought about that too. You're like, oh, crap.
So one of the things that he says that I really have taken to heart. I mean, I said earlier that he talked about quantum mechanics. Nobody understands quantum mechanics. But he did offer a kind of a picture. He said, it's as if the universe is divided into a couple layers. And the top layer, the one we live in, is material objects and their relationships, things that we can see and understand and manipulate. And that's one level, and that's a level where you work with real materials and real things. But he said under that, there's another level, the quantum mechanical level, which mostly concerns very, very small objects. He said, which is really inaccessible to verbal or picture or model building forms that can only be approached mathematically, he says, which my heart fell at that point because I thought I'm never going to get there if it requires partial differential equations. I barely remember algebra.
Yeah.
It says also that you can't make analogies; they never work. And I remember thinking to myself when I read that, "We'll see, Mr. Feynman. We'll see. Maybe we can do." And then later on in his lectures, he starts making analogies. So I know it's going to be possible to at least get a little way into this subject. Enough for me and the book I'm writing to explain to fellow amateurs in the field of physics sort of what's going on when we're doing these things and what they're about and why. That much I think I can do. This is a horse of a different color from nuclear physics entirely. When I started working on my books about the bomb, I didn't know any nuclear physics, but I very quickly, and I had the same sinking sense of I'm never going to know what I'm writing about here. But I very quickly, as I got into it, realized that nuclear physics was almost entirely an experimental science, which is to say, most of the important understandings that came along were based on laboratory experiments, which is to say, someone made a box out of brass that could be sealed so that you could exhaust the air in it. And then they attached something to one end that naturally, spontaneously, a little piece of radium, let's say, gave out particles. And then they attached something at the other end that could detect those particles. And they exhausted the air, and then they did this and did that. And when you read the paper, it basically tells you what they did. I built this box, and I put this in it, and I put that in it, and I measured this, and I got this. And this means this. And there's very, very little math in the papers, the fundamental papers of learning nuclear physics, all the way up to the bomb, because the bomb was not even physics, as Oppenheimer famously said. We didn't do any physics from 1941 to 1945. And he meant by that with the exception of measuring a few fundamental constants that no one had gotten around to measuring before, that were useful in understanding how bombs work, how nuclear weapons work, there really wasn't. This was high-level engineering, basically. They had to figure out how to make a little ball of plutonium get squeezed tight enough to chain react, and then off it went. So it's nice to hear Feynman saying there's another level under the level we're all familiar with. It helps understand why it seems so impenetrable and arcane as it does. And then when he starts talking about how particles interact with each other, you realize that that's pretty clear too if someone is competent enough to explain it clearly. And fortunately, I've already found some of the people I interviewed at CERN in Switzerland who've written books about the building of these giant machines that they operate with, who are wonderfully clear in their description of the machines and what's involved and so forth. So it's going to be possible. I think the first step in writing a book is it even possible to assemble this story and put it in a meaningful order that other people will be interested in reading about? And the answer is, yeah, it is. At least I think it is. And just as a backup, I've signed up as a consultant professor of physics at the University of Wisconsin, a wonderful woman named Shelley Lesher, who's a nuclear physicist, but she's going to help me with my particle physics if I ever get stuck. She knows the math and I don't, so I'll have someone who can maybe dig me out of a hole if I get in one that I can't get out of.
Yeah.
You've seen these videos online where some poor animal falls down into a hole or gets stuck in a river or something, and then all sorts of nice people go in and save them. That's Shelley. She's going to be my rescue team.
Yeah. And then the animal goes and falls right back in the same hole. Yeah. But there is, I mean, I always remember, at least in college, taking like organic chemistry or genetics or something. You would start it and it would just seem so alien. You know, you understood general chemistry, but then you'd get to organic chemistry and you'd be like, this is, as you said, it felt impenetrable. But the more you just had to hit it again and again and again. And sometimes you go days where you don't feel like you're making any progress, and then all of a sudden you start to recognize puzzle pieces, and you go, oh, that can fit there.
Right.
That can fit there. And then if you keep the repetition going further, it starts to click. And then the final form of understanding is, can I explain it to my friend who's struggling? And then
Yeah.
that forces you to break it down even more and go, it's as simple as Bob has 5 apples, he gives 1 to Susie. How many does he have? And when you can get there, all of a sudden this thing that seemed exotic and SN1 and SN2 reactions and hyperconjugation, and you're looking at it and you're like, what is this? And if you push hard enough, it starts to click. And then you start a
Yeah.
new chapter and you go, I'll never understand this. But if you keep moving forward, you do. So I imagine it could be done. And that's a confident statement, because if Richard Feynman said it, you can't understand it, then, maybe we are hitting a ceiling. But I think it's we have eyes and ears, and we can examine this, and we have equations. Like we will extrapolate and we will understand it. The Wright brothers flew like 120 feet, but I mean, they took a heavier than aircraft and went airborne. Maybe not tomorrow, but I would imagine someone around there was like, it'll take a while, but one day you'll be able to fly over oceans. Not now,
Well,
maybe.
yeah.
So
And remember, Wright brothers flew gliders for several
yeah,
years before they flew something with a motor in it,
yeah,
with an engine in it, because they learned all about how wings work by their glider work. And in a way, Feynman talks about that. He talks in his wonderful, simple language about how you come up with a new idea and test it, a new theory. He says, you guess. At first, you just guess. You think maybe something will work, and you put it down, and it sort of is, and maybe it's not. But ultimately, what you end up doing is doing an experiment. He also says you can never definitively prove that something is true in science. You can only definitively prove that it's false. Because if you show that some theory is absolutely wrong, it'll always be wrong, no matter how many furbelows you add around it, how many Elizabethan collars you attach to it. But but he says if you find that something is wrong, it's going to be wrong forever.
yeah,
And if you think something is right, there's always the possibility of more information out there that you didn't know. And therefore, he's really good about this in this little book. I recommend it to anybody. It's what's it called? Hang on, let me find the title, because
yeah.
I
You're
think
good.
people should look it up. They'd love it. Where did I put it? Well, I'll find it before we're through here.
It's
Uh, when he talked, but what he does say about this underlayer, this quantum layer of reality, which is so strange that something could go through 2 places at once and come out the other side without our being able to prove that it can't do that, or find a way to catch it in the act, go around behind and check it out. He goes through all those possibilities. He says the only way you can really approach quantum mechanics is through mathematics. And he says something very interesting about mathematics. He said, people always say math is a language. And he said, yes, it is a language, but it's more than a language. He says, it's a collection of solutions to problems that people have worked out and assembled together and linked together over centuries. And as such, it's more than just a language. You can't just learn to read it and understand it. If you want to use it, you actually have to learn it by using it.
mm,
And therefore, people who don't have math, he says, this is where I bridle, of course. Fools walk in, as they say. People who don't have math really can never understand it at its full depth. And I don't know, maybe that's true. Fortunately, I don't have to. I just have to understand it well enough to explain it to my neighbor,
yeah,
so to speak.
yeah.
And if they want to learn all that stuff, well, they're probably younger than I am and have time.
It is. You almost wonder then, like, are we? It's almost like, it's kind of evoking the idea of Carl Sagan's Flatlanders. You know, the two-dimensional being viewing a sphere as it comes through, and it's just like a circle that gets wider and then smaller, but they don't see the sphere, and they really probably can't comprehend it. You almost wonder if our interfacing with quantum mechanics, and I'm sure this is not an original idea of mine, but you almost wonder if our interfacing with quantum mechanics, how it makes no sense. Superposition, things popping in and out of existence. They're still and they're moving at the same time. They're both a wave and a particle. They're both up and down. They're positive and negative. They have no mass and all the mass. They're going forward and backwards in time. You know, like, and you look at it and you go, this makes no. It's kind of like viewing like the accounting. It's like seeing like a store and it's been open for years and there's no customers. Eventually you go, they're laundering money. Like, something's going on there, right? It doesn't make sense. There's something you're not seeing.
That's a good analogy.
I wonder if that's what quantum mechanics is we're not seeing it all. If it seems so alien and it's so, because like you said, even nuclear physics, and as daunting as nuclear physics is, if you go get like a beginner's book and start looking at it, you can kind of, you go, I get the general idea. I could maybe pass like a kindergarten test. Sure, we're hitting this and then this decays and it falls apart. Okay. But like you said, quantum mechanics it's almost this weird, fictional, philosophical, it's all very fuzzy. At best, if you're a mathematical genius, which I'm not, I failed pre-calculus 3 times in college, somehow still got into medical school, but failed 3 times. I wonder if we're interfacing with perhaps the edge of not only our understanding, but also our consciousness, which we thrive in 4 dimensions, X, Y, Z, and time. I wonder if we're interfacing with a 5th or a 6th dimension. And no, we won't understand it because we can't. I mean, I don't know.
Well, I think that's really where Feynman helps clarify what exactly it is, because quantum mechanics, particle physics, works all the way out to like 6 or 8 percentage points behind the 0 point, behind the period in a, what am I saying, in a number.
Decimal point?
It's extremely, yeah, decimal points, places. It's extremely accurate. Once you accept the fact that there are certain things that you have to just set aside because they discovered in the 60s as they were working on it that the theory basically worked in a particular context experimentally, but that if you tried to do some calculations, your numbers ran off to infinity, which told you immediately that something was radically wrong about the whole model. The solution was to what they called renormalize, which was basically to say, okay, let's play a few mathematical tricks and pretend that doesn't happen, and then see where we are. And when they accepted that there was part of the model that wasn't going to work, the rest was just gorgeous. One of the things that was missing for a long time was a particular particle, was the question of where do things, material things, get their mass? Mass is the amount of matter in a body. Weight is a mass accelerated by gravity. That makes sense. So when we talk about weight, we're talking about mass, but we're talking about a mass that's falling or being thrown up. That's where we get the concept of weight. So mass is not exactly weight, but it is the amount of stuff we have. Okay, so wait, where was I going with that? Oh, anything. Lost my train of thought. Happens a lot, unfortunately, especially when you're just learning something. You just drop out for a while. I was talking about
everything working except for parts of the model.
Yeah. There was a question in quantum mechanics about where do things get their mass? What is it? I mean, quantum mechanics works basically sort of with particles. Let's talk about particle physics, and I'll be simpler here. Particle physics basically says that interactions at a distance take place by the exchange of particles of various kinds. I'm over here with a lamp, you're over there. I shine my lamp on you and I can see you. I see you because photons from the lamp go over and illuminate you. And my eyes pick up those photons and so forth. Okay, so the interchange that goes on that makes things what they are is served by particles. So what's the particle that gives things their mass? That was not known, and it was a big problem, a major problem. Back in the 60s, there was a very shy, quiet Scottish physicist named Higgs who worked out the idea that there must be a very heavy particle, a boson particle, which has mass, that is the particle that supplies everything in the universe with its mass. Well, in order to create that particle, they needed really high energy accelerators, and they didn't have one yet. So there was a race between American accelerators like the one at Fermilab, which was being built up and then was switched around to become a collider to get more energy, because everyone wanted to be the first to discover this absolutely essential last piece of the whole, what's called the standard model of particle physics, the one big missing chunk that this quiet Scottish physicist had thought up, but had not been able to do more than just say, there has to be such a particle, and if there is, it will probably weigh at least this much. He didn't miss it by much. He guessed a little high. I think he came out with 150 something. Anyway, we didn't have any machines that were powerful enough to produce that Higgs boson. And there was a race on in the United States and in Europe and elsewhere to be the first to make that happen. One of the things that followed from that was that there was a big movement down in Texas at the University of Texas to get the government to build a huge collider. It was called the Superconducting Super Collider. It was going to be built in Waxahachie, Texas, which was the district of a particular congressman whose vote was needed to get the money released, because it was going to cost like $20 billion, right? Anyway, it was a very conservatively designed machine. It had superconducting magnets, but it didn't use some of the more sophisticated technology that was even then available. I don't know why. I do know that my former Cambridge, Mass. landlord, Stephen Weinberg, the Nobel laureate theoretical physicist, was partly behind this project. And it was eventually dumped when it was they dug these giant tunnel rings. It was going to be like 50 miles in circumference. So it would have been like twice, 3 times the size of the LHC in Switzerland today. So in the 90s, it finally collapsed of its own weight because Congress basically could say yes or no. And at some point, with the overruns on costs, digging this giant tunnel, it got killed. And it was a great blow to American physics because it took us out of the running for being able to be the first to produce a Higgs boson. At which point, the Europeans started working on this series of colliders that led to the Large Hadron Collider, which was specifically produced with the hope that they would be able to get Higgs bosons out of it. And in 2012, they did. They finally were able to show it's really a strange particle because it's very heavy, several thousand times as heavy as a electron or a proton. Mm-hmm. And it only, when one is created in a particle accelerator or by a cosmic ray or whatever, it's only around for less than a trillionth of a second before it disintegrates into a whole bunch of other particles. So you can't find it. All you can find are its decay products. And those you can specify and identify. So they had to run this collision process several million times You understand when they're running the collider, they're getting like 10 or 20 collisions every second. They have little packets of particles that are spinning around this giant ring, being accelerated as they go. They're separated by about a foot between each little punch in this vacuum tube that they're spinning around in. So it's a series of collision, boom, 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 and each one is then measured as the particles go flying. So they were, in order to get a statistical proof of this particle's existence, since they couldn't actually show it, they had to run this thing several million times around. And what they got then was a graph that showed basically a steady line of collisions. And then in the middle, there was a little blip. And that was where the Higgs appeared. So even now in the papers, they say a particle with all the characteristics of the Higgs shows up in this graph at such and such a point. It was like 127, whatever these units are. It wasn't 150. That would have been almost beyond the reach of this big machine. So they lucked out in terms of it was a little lighter in weight than they were afraid it would be. They were worried it would be like 300. And then nobody would have a machine big enough to do it unless they built a really huge one. And I guess maybe that's what this new 100-kilometer job is going to be. They're going to be making a lot of Higgses on the new machine, just as when the neutrino was first researched. You were lucky if you could catch one of these neutrinos in the course of a year's work. And now we've got neutrino factories, machines that just crank out neutrinos day and night, and they're using them as basically as probes for other reactions that they're interested in. One of the things I like about science is that today's new discovery becomes tomorrow's technology.
Yeah.
You know, the Robbie, the physicist I was mentioning, this guy who grew up in New York and was such a brilliant and generous man who worked on the bomb. Robbie did his Nobel Prize work studying the magnetic moment of particles. And I can't even explain what that means.
I remember the
but
term,
the machine
but that's it.
he developed, the machine that he developed to do that is now the familiar MRI that we have in all of our hospitals for measuring health issues for people. So there was a really practical result. Here was a machine that didn't have to irradiate you with radioactive materials. It would just flip the magnetic moment of some of the particles in your tissue and find a way to record that, and then with a computer reconstruct the form of the organ or whatever this is being studied. So Robbie did, that was pretty typical Robbie work. I mean, he did things that in the longer run ended up really benefiting humanity, which was his purpose anyway.
I mean, isn't that how the microwave came about? They were testing it for something else, and one of the researchers noticed the chocolate bar in his pocket was melting. And he was like, "What?"
Everyone who has a microwave in their kitchen has a little radar unit in their microwave.
Yeah, that's what I
The
mean.
original, it was a type of cavity magnetron, it was called. And it was the tube that the British invented in the late 30s and brought over and handed to us free of charge, patent free, in exchange for our helping them work on radar. So then someone discovered one day that if you walked into the beam of a really powerful radar, you could fry your eggs, and realized that there was a lot of cooking energy coming out of these things. And as they got smaller and smaller, they're now what's in every microwave in the world. Yeah, it's a radar unit.
Yeah, and
I like that connection because science seems so alien and exotic to most people. But if you think about it even a little bit, you realize just how much it's everyday part of our lives. And I don't mean these unbelievable magic screens we all deal with these days. I mean as simple a thing as a lever to pry open the lid of a can of beans.
Yeah.
That's we studied levers, right? We
Yeah.
studied levers. They're
Yeah.
complicated and interesting objects.
Yeah.
And at every level in the world we live in, and particularly today, science is at work making our lives a little bit easier.
Yeah. It's
There's a wonderful book by a writer named Elaine Scarry that, and I'm trying to think of the book title, but she talks about the ability of ordinary objects that we create with our imaginations to alleviate human suffering, and says that the really deep function of invention and creation and science is to ultimately alleviate human suffering.
Yeah.
And she uses a familiar example that philosophers always use, which is a chair. A chair is anonymous. Who knows who invented the first chair? Nobody. It's not like a symphony, which has to be performed in order to be in the world, or a painting, which has to be looked at in order to be in the world. It's just this thing that but what does it do? It alleviates us from the pain of gravity.
Yeah.
It allows us to sit down and be comfortable. And that's true of beds, and it's true of, the food that the farmer grows,
Yeah.
and on and on and on. These are all products of the human imagination. But the little anonymous things, in a way, are much deeper and more profound than
Mm.
the great creations of humanity.
For now, and then a million years from now, they'll be like, no one knows who discovered the Higgs boson, but and that's how we just keep moving forward. Though we're just kind of reaching up on this scaffolding and then standing on the
Yeah,
shoulders of giants who are standing on the shoulders of giant. Yeah, you got to almost, we've talked about these like momentous moments in human history: standing upright, the opposable thumb, moving from nomads to an agricultural society. Yeah, what I hadn't thought about that till you said it. The chair alleviates you from gravity, and I just had this image in my head of like the famous statue of the thinker, like he's sitting, like that's.
yeah,
I
yeah.
mean, I wonder how much that had an effect on just the size of the brain over eons of time. That you were able to sit and think. When you really got to think, when you're really studying something hard, what do? You lean back in your chair and you're really, it's almost like you're releasing, you're not flowing blood to all your muscles. You're really allowing it to go up to, you're like, come on, what are we
It's
doing?
true.
Yeah.
Yeah.
And
Well,
that's,
and at one point, I can't quote it exactly, but this is almost exact. She says, humble objects, humble anonymous objects may not seem very glorious, but they basically exist in the world to say, I'm here to help you and I wish you well.
hmm,
It's a really lovely
I
idea.
like that.
Yeah. And then, of course, we shouldn't forget the other side. And this is what we've talked about when Niels Bohr arrived at Los Alamos as Vicky Weisskopf, who, by the way, was the director of CERN after the war for about 5 or 6 years. When Weisskopf said we at Los Alamos were pushed into the darkest corner of our beloved science, meaning they were working on weapons of mass destruction, and it worried us and troubled us. Bohr arrived and Bohr gave us a larger sense of what we were doing. And what that sense was Bohr saying, look, one side of what you're doing is certainly building a weapon that can kill a lot of people. But at the same time, you're probably going to make it impossible for world scale war to continue hereafter.
Yeah.
Because you're going to make it so destructive that people will not be prepared to use these weapons as soon as more than one country has them.
Yeah.
The United States was able to use its nuclear weapons because there wasn't anyone else threatening to do the same in return. And as soon as the Soviet Union got its bomb in 1949, that was a different world. And since then, it's been a very different world. It's just absolutely remarkable to me that no one has used a nuclear weapon in anger since 1945.
Yeah.
I only got to talk to Feynman once when I was early on in my working on the making of the atomic bomb. He was out at Caltech at that time, and I was on the East Coast. I was living in Connecticut. I couldn't get out to see him in person, but I called him and did a kind of an interview on the phone. It was interesting what he said. I said, what were you thinking right after the war? how did you feel about the whole business with the bombs now in existence and so forth? And he said, I was sitting in a bar. He used to go sit in the bar and drink Cokes and pick up women. That was his other side of his life. He had been deeply in love with someone ever since he was a boy. They had married, and then in the last months before the bombs were finished at Los Alamos, his wife had died of tuberculosis at a hospital in Albuquerque. And after that, he was kind of I think he must have decided for a few years, I don't ever want to be close to anyone again, because he was a really good looking guy. He was witty and funny. He'd go into a bar and sit and have a drink and pick up girls and take them home. He did that for quite a while until he got himself back together. Not surprising. Anyway, said I was sitting in a bar in Times Square on an afternoon in 1946 and looking out through the glass windows of the bar and thinking at the crowd outside milling around, thinking, you poor fools, you have no idea. You only have a few more years to live. And then the whole world is going to blow up. Because there was a general sense that these bombs would lead, once another country got them, to a war with nuclear weapons. And that would destroy everything in the world, which indeed it would have. But that's not the way it happened. And Bohr saw that even before the end of the war. And was able to help the guys at Los Alamos, you can say, rationalize what they were doing. But the fact is, he was seeing what he always called the complementarity, that there's never just, this was kind of a quantum idea that Bohr was the original quantum guy. He did the first work toward developing quantum theory back in 1913. So he spoke with some authority about this idea, which to him was not just a physics idea, it was a philosophic idea. And that is, it takes more than one side of something to make a whole. Yeah. You can't just say, I've got this part and that's all there is. This is a negative truth and that's all there is to it. There's a positive truth as well. And that the only way you can really find it out is to look deeper into this thing. How did he phrase it? He said, every great and deep difficulty bears within itself its own solution. And that was what he took to Los Alamos and made people like Weishaupt feel, oh my God, well, there is some hope with what we're doing, that maybe in the longer run, we will actually reduce the number of man-made deaths from war in the world, which is what has happened.
They did.
There have been, the highest point in the number of man-made deaths from war in the history of the world was 1943, when between deaths in battle and collateral deaths of civilians and the Holocaust, 15 million people died that year. 15 million people. Then the number started to go down. And in 45, it was down to about 2 million at the end of the war. And it's never gone above about 1 to 2 million ever since. I like to say that's a terrible number and it's nothing we should be proud of. But we lose 7 million people a year from smoking. So in a sense, we were kind of inoculated by this development in physics, this obscure development in this obscure science, from something that had plagued humanity almost as bad as smallpox since the beginning of time.
And it had been...
when you think about quantum mechanics as something where something is neither a particle nor a wave, you see Bohr's idea at its barest. You can't just say that this thing is a particle, and you can't just say it's a wave. It's both at the same time. You can't just say the bomb is evil.
A weapon, yeah.
It also did it at the same time.
That's beautiful.
Isn't that beautiful?
That's incredible.
I love that.
That's incredible. Yeah, what? That
so
is,
even though I have no
Wow.
idea what the Higgs boson is going to do for us, whether it's going to put any cornflakes on the table anytime soon, who knows?
But it will, and the fact that we don't know, it's like I think Alan Watts said, the answer always lies in the last place you look for. I mean, by definition,
Yeah,
because you find the answer and you stop looking for it. We can't know. If we knew, it wouldn't be research. So
right.
we're in the dark and we're reaching around for something. We don't know what we might find a bar of gold, we might find a hamburger, we might find a kitten, who knows?
Right.
But
Right.
for the last 10,000 years, it's shown time and time again that some obscure field results in penicillin or plastic or whatever, or inoculating us against thermonuclear destruction. We don't know. We're reaching out for something, and we'll find it, and then we might not know for a century, but you'll look back and you'll go, oh yeah, sure, that's the thing. And
And the other side of that, and the other side of that, and it's one that has really plagued a lot of our world for the last 200 years, is the progressive. This is something Bohr used the phrase. He said, science is not about power over nature. It's about the progressive alleviation of prejudice.
oh,
And, and for example, it was a prejudice that the Earth was at the center of the universe back in Galileo's time. And when he and Copernicus were able to show that the Earth went around the sun, it was a disaster for the religions of the day. And Galileo and Copernicus got punished for it royally. So also with the Darwinian realization that we evolved, like all the other mammals and creatures in the world, through a process that he called natural selection, which is still under debate in religious circles about whether you can accept that, or are we just, did we really just come from the monkeys? No, we and the monkeys came from another smaller creature indeed. It wouldn't have happened if the dinosaurs hadn't been killed off by an asteroid, and so forth and so on. So Darwin and all of that is still under consideration, if you will, by our civilizations,
sure.
but pretty much generally accepted. And there's more to come. Well, E.O. Wilson, about whom I recently published a biography, the Ant King,
Yeah, scientist.
in one of his wonderful books, he says, we're gonna. He was an optimist about where we're going to go. We're gonna deal with global warming. We're going to deal with population and it's being reaching too high and so forth. But he said at the end of all of that, we're going to conquer all the diseases eventually. We're going to find out how to treat them and take care of them. But as he says, at the end of that, a couple hundred years from now, we're going to be left with the truth that we're just mammals. We weren't put on Earth for any particular reason except to reproduce our kind and go on and reproduce our kind and go on. And he says that's going to be a real spiritual crisis for humanity. But we've weathered other spiritual crises already. So presumably we'll find a way to deal with that one.
I
The
think
point is, once again, I mean, here's a Bohr sort of all of these wonders. We deal with global warming. We conquer the population explosion. We get rid of disease and live out our full lives in good health. But then we find out that we're not demigods. We're just another kind of mammal. We just learned to walk on our back legs.
it's to quote Alan Watts again. Yeah, once we have infinite renewable energy, nuclear fusion, no war, no disease, no prejudice. Yeah, everything's done by robots, and we can create a utopia. And then we have the realization that what are we doing? I think of Alan Watts, and he goes, "The purpose of life is just to live." He goes, "Life is like a song. You don't start a song with the intention of getting to the end of the song." Because he goes, otherwise the best songs would just be a single note. He goes, no.
That's beautiful.
Yeah, you
That's
listen to a
beautiful.
song and you
Yeah.
dance while the music is playing.
And to jump back to Elaine Scary, the song only exists when you're performing it.
Yeah.
It's a special class of object that has to be performed in order to be in time. Whereas the humble chair is always there waiting for you.
Yeah.
Her point was that was one of her points.
Yeah.
Um, what was I going to say? There's something related to this. Forgot. Anyway,
It'll pop up next time. Yeah, it's
yeah.
no, I think, I mean, I guess we'll kind of wrap it up with this is like, we didn't set out on this particular podcast to reach a point. We didn't set out and say let's make it to 60 minutes. No, you just let it flow and you bounce around and we had some laughs and some realizations and then it's over and you enjoy it and you don't go, "Oh, I wish we could redo that." That's just what it is.
Well,
And
I do wish I didn't have to go back to trying to understand particle
well,
physics, but
unfortunately, you do
that's
because you're Richard Rhodes, and that is your job, and that is your burden. I get to do podcasts. You got to do research so I can listen to the book, and
because I
yeah,
have a bargain. Because I like to tell people when they say, "How do you get up in the morning and go in and work? What motivates you?" And I always say, "I have a mortgage."
well, maybe yeah. So, is a mortgage a good thing or a bad thing? I don't know. I get to read your books, and your books are out in the ether for all of humanity to enjoy. If I had the
Of
ability,
course,
I don't know if I'd pay off your mortgage because I like your books. So I think the ball and chain is actually doing a great favor to humanity.
clearly it's more than that. But
Yeah.
it's funny. I've known enough people who had some money who really had to struggle to get books out. They weren't motivated. I mean, it's hard to write a book, even if it's hard to do anything well. And books are like building elaborate pieces of cabinetry with all sorts of filigreed pieces moved in to make a picture. So I can see why people have struggled with it. I happen to enjoy it, but maybe I'm a masochist. I don't know. Anyway, I
Well,
like learning, and that's what the aspect of writing that and the craft of putting things together. But for those who don't enjoy that much, if they have any other source of income, they have trouble getting books done.
yeah.
It's very interesting to see the phenomenon, for example, of people whose first book is a bestseller is very interesting.
Mm.
They often just fade off
One
into the
hit wonders.
sunset.
Mm.
Yeah,
Yeah.
I'm very grateful. My first book was my first important book was a novel about the Donner Party, and it was almost selected as a main selection of the Book of the Month Club, which would have meant an immediate 100, 200, 300,000 copies were sold. So fortunately, there was one member of the judge panel who was a Westerner and who was mightily offended that anybody would tell this people going west eating their dead. And he voted it down and it didn't get included. So I had to slog on and write some other books. And here I am.
Well, like the particle or the wave, is that a good thing or a bad thing? It has led to all of your books that I thoroughly enjoy that make me ponder life. I don't,
Thank you.
and um, I just kind of a thought about what drives you to work. I've always had that worry about like what if this show succeeds? Do I stop working? And then I look at my parents who just worked themselves ragged, raised four children, and finally retired in mid 60s, and they went and retired up into the woods, and they work just as hard as they're chopping wood. They have their own well. They're planting. They're gardening. They're building. And
Yes.
now I look at it. I'm like, no, I don't think. I think for some of us, I know it's for me. It seems to be for you. I know it is for my parents. There is a bliss in taking on huge projects and just devoting yourself to them and perfecting them and moving on to the next.
That's
It,
a, there it is.
yeah,
It's a kind of lifetime learning, and it's
yeah.
really, really deep and wonderful
It's
because it's cumulative. The more you learn, the more you can learn. You have more ways to look at things because of what you've already learned.
yeah,
So in that sense, it's just the accumulation. By the way, one thing we should talk about next time we do this, which I
sure,
hope we will do,
sure.
uh, I've been thinking about for many years about a book that would tell the story of the eradication of smallpox,
Oh, that'd be
which
great.
was one of the great of humankind. But there's a twist at the end, and I'll just give you a taste of it. After smallpox was eradicated, with the cooperation of almost all the governments in the world, including the Soviet Union at the height of the Cold War, they donated a lot of vials of vaccine and so on. we contributed money, of course, being Americans, and also people who led the program. But and I got to know the guy who ran the program pretty well. He just died a few years ago. Uh, After the whole thing was done and the Cold War ended and the Soviet Union collapsed, it turned out that the Soviet Union's motivation for helping to eradicate smallpox
Oh
was to
yeah.
get the world to no one had any immunity
Yeah.
because they've been developing a bioweapon, a weaponized form of smallpox. And Henderson, D.A. Henderson, the man who ran the program for this country, was so horrified by this kind of O. Henry turn to the story that he started a whole U.S. government program to deal with bioweapons and the whole problem with bioweapons. That's the next problem with atomic bombs. It's already at the point where smart high school students can do genetic manipulation in their home laboratories.
Hmm.
So, and the scale of materials that you need are very small compared to what it took to build a bomb,
Hmm.
compared to what it still takes to build a bomb.
It's
So that's an interesting subject. And the smallpox story is itself an absolutely fascinating story about how humans handle problems and don't handle problems,
that's
run away, and so forth.
yeah, that's
Think about it.
well, that's another. Well, it's just
Not-
there's the other particle on the wave. You know, is the
Yes.
Soviets' desire to have a smallpox bomb bad?
Yeah.
Well, it led
Yeah.
to the eradication of
Yeah.
smallpox. What happened to the Soviet Union? Oh, then they fell apart. I don't
But
know.
this little secret lab was still going on after it fell
Well,
apart.
I've
And who knows, probably still is.
I've interviewed several times the first director of that lab, Dr. Ken Alabek. He headed up
Yeah, that's
BioPreparat.
right. I have his book right now and I'm reading it.
It's so good.
So you know
Biohazard.
that story.
I'll send you the
Well,
episode I
I'll
did
fill
with
it,
him.
which in itself is an amazing story. Good.
Well,
All right.
we
Back to
went
particles and waves.
25 minutes
Here's a
longer.
wave.
A particle in a wave. It's trying to slip in your dad jokes in here. How dare you, Mr. Richard Rhodes? Thank you, sir. I will put all the links to your books, your website in the description. Guys, if you like this episode, go watch the old episodes with us, and certainly go read his books, listen to them. They're on Audible. I believe you. I know that you narrate Dark Sun because I've listened to it so many times. But I love all of
The earlier
you.
books.
Yeah,
Yeah.
they're all great. And I'll text you right after this, and we'll schedule another one, and we'll do a smallpox episode.
Okay.
Thank you, Mr. Rhodes. Thank you for your time. Thank you for listening, everybody. God bless. Take care. Thank you
Recording
so much.
stopped.
Peace.